Alright, welcome. In this video we're going to take a look at one algorithm, although we're going to look at one concept or one idea, the idea of edit distance. Now edit distance is how many edits it might take to change one string into another string. So we use this in sort of a string handling type way. Now edit distance can be used in many different ways or different purposes, but usually it's used to measure the similarity between two strings. So a very obvious way this could be used is to suggest possible correct spellings of a misspelled word when you're typing it in any kind of word processing device. So let's take a look here a little closer at this idea. So actually, the idea of edit distance has its origins not in computer science, in linguistics and in other sciences have studied this beforehand. And so here we actually have Vladimir Levenshtein, who is famous for at least popularizing one way of measuring the edit distance between two strings. Vladimir Levenshtein considered three different edits that you might perform. He considered insertion, deletion, and substitution. And actually, before we get into his method, and here we are asking to what is the minimum number of edits, let's actually go and explore this a little bit more with our two strings. Alright, so we have these two strings that we're considering, bandana and Montana. And let's for the moment consider that we're trying to change Montana into bandana, although the reverse process is really exactly that, just reverse. You can usually do the same operations backwards to get you back where you were started. So here we just want to go from Montana to bandana. And one thing we're going to notice, and actually for the moment I'm only going to consider two possible operations. Let's consider insertion and then deletion. If we only consider these two operations, then we're going to see that there's actually our sequence. Remember our longest common subsequence here, nana, is an important sequence for us in this case, because if we want to do this, what we're going to have to do is we're going to have to delete these characters and then add in these characters. So we delete out all the characters that are not part of the longest common subsequence. Remember, longest common subsequence. Let's call this the longest common subsequence of A and B. Let's say the length of it. Okay. So what we could actually do here is, if this was our string A up here, the number of deletes we need is going to be the length of A minus the longest common subsequence of A. So the length of A in this case, let's maybe keep track, was 7, and the length of the longest common subsequence was 4. So here we have 7 minus 4. That's how many deletions we needed. These were our deletes. So then we also need to do insertions, and the number of insertions we need then is also going to be, we have the longest common subsequence, we don't have to do that, the other one, so it's going to be, so we're adding on now, the length of B minus, again, the longest common subsequence of A and B. Okay, so again, length of B in this case happened to also be 7, minus 4 again, add on, these were our inserts. So total here looks like we got 7 plus 7 is 14, that's minus 4 is 10, minus 4 more, looks like 6. 6 edits. Okay, so we can use 6 edits to change Montana into bandana if we use only inserts and deletes. And in fact, this formula that I've got here, which, well, we could write that a little bit easier. Let's write it a little better down below. Length of A plus length of B minus 2 times the longest common subsequence of A and B, since we minus it off twice. This could be a distance measure between A and B. It tells us how many edits we need if we only count inserts and deletes to change A into B for any strings A and B that we've got. So one of the reasons why the longest common subsequence is an important tool or important algorithm that we use in other cases is this tool allows us to see the edit distance. How many edits would it take to transform one string into another? And this tool actually is used in a couple of important places. Some of you may know this. There's a command in Unix-based systems called grep, which will go and find certain substrings, and built into that it will have this one. But more commonly, we have a way of comparing two files to see if they're equal or not, or different or not, and they're usually, it depends on your operating system, but there's usually a method that will compare the difference between two files. And what they do is they find the longest common substring and then find it, any difference. This might also be used, for instance, in when you're trying to merge code together. Finding the difference between the two files is finding, the longest common subsequence might be what we have in common, and then everything else might be what we need to merge. So there's lots of different reasons why we might want to use this in practice, and so we can see that this distance measure might show up in some of these. Okay, so this is one place where distance measures show up. One other place where they show up actually, and this is one area where I use them a little bit, is in genetics. Actually, I do a lot of biological simulations, and most of my genetics are fake. But in the real world, all genetics, at least as far as I'm concerned, as a computer scientist, our DNA is only made up of 4 symbols. Now, there's actual chemicals involved, and there's probably some chemistry and biology that I don't really think about very much involved. All I think is there are 4 symbols, and those symbols are part of an alphabet, and they end up making strings that spell out, well, our DNA, our genes, or whatever it might be. So there's a lot of different uses for string handling algorithms, like the longest common subsequence, involved in trying to compare genes or DNA sequences. Say, for instance, you have a particular gene that you know is helpful or not helpful for whatever reason, and you want to know if someone has that gene, you have that gene maybe, then what we want to do is we want to look at your DNA sequence, which is very long, and maybe see if it has this particular gene in it. So we might be, again, performing an algorithm like longest common subsequence to see if it contains this subsequence, the one that we're looking for. So these edit distance tools are used in different areas, different sciences as well, for different purposes. So it's not just the means for studying an algorithm design technique, which is really why we have it here today, but it is a tool after we use that. So I use this in a number of my algorithms to measure the distance between, say, 2 artificial creatures that have artificial genetics. Okay, so let's maybe go back here and again take a look here at what Levenshtein did. Actually, maybe let's do one last example here. That Levenshtein says not just considering inserts and deletes, because that's what we have here, but let's consider instead insert deletes and what he calls substitution. Now, substitution allows us to take one character and substitute it out for another. So we could swap the T for a D. And we'll see with our special example here that we actually have one character for character swap out. That's actually very lucky for us. So we did 6 edits when we did just inserts and deletes. Well, if we add substitutions in, we don't need to do any inserts and deletes, only substitutions, and we can get away with 3 edits. So there's actually only 3 edits to change these two together if we allow ourselves substitutions. Now, at Levenshtein, his original edit distance included substitution, but we could imagine also including maybe some other operations as well. One of the reasons why he was studying these was, again, for maybe typos or errors we might make in spelling, And a very common error made, at least when you're sitting at a keyboard, is to swap two characters. So two characters that are right next to each other might be transposed, swap position, and that's very common. Say a very common spelling error is T-E-H instead of T-H-E, and that, of course, is one that should be easily spotted and corrected. But if we allow the swap operation as one of our edits, then that's only one edit away instead of two edits away if we don't allow it. So all of our edit distance provide us with different measures of similarity and difference between our strings. And again, depending on what purpose we might be using this distance measure for, usually indicates which one we're going to want to use. So we're going to look at the last one here, the edit distance related to Levenshtein's edit distance. And well, he's famous for coming up with a recursive definition that we're going to look at in a second, and then popularizing it. Although he, as a linguist, was not interested in the algorithm so much. I think if he used it, I'm not as familiar how he used it, but if he used it, he probably computed it by hand, recursively. Meaning, if you do it recursively, you can be a little bit clever about it and maybe notice, carefully select the path that you're going instead of doing the overlapping subproblems if you're doing it by hand. I imagine that's how he might have used it. But if you ever wanted to automate it, then you would know that the recursive definition is inefficient and you might want a different way to code it up. And so actually the algorithm, the dynamic programming algorithm that we're going to look at in more detail, is commonly called the Wagner-Fischer algorithm due to some researchers who came after Levenshtein to use his definition to come up with their algorithm. Okay, so I think we answered our question here about the edits to transform. So let's maybe quickly, once again, one more time, look at the dynamic programming design techniques. Well, we want to state the problem as formally as possible. We haven't actually done that yet. Find some subproblems. Well, let's look at the last two problems we looked at, longest common subsequence, longest common substring, where this problem has a very similar structure. Okay, so we can think of it as a variant. We're going to change things a little bit. It's a further step away than the other two were, but it is still a variant. So we're going to use that to inform our self-reduction. And indeed, we will identify some overlapping subproblems. And then being careful with our dynamic programming, we want to make sure that we're doing bottom-up, not top-down, no recursion involved. We're going to fill up an array with some solutions to subproblems. And in this case, we're talking about two-dimensional problems, so we'll look at a two-dimensional array. Okay. All right, let's start by just formalizing the problem as that's step one. So we want to come up with a definition of our edit distance. And so our input, again, is going to be similar as we've seen for our last two problems. Let's set it up as just two lists, A and B. And we could call them lists or sequences. I'm just going to call them sequences of characters. Our output then, well, again, this is an optimization problem. I'm going to call it E, is the minimum, in this case, number of edits to do what? To transform A into B. So that's how many edits. We still need to know how to do that. So I'm going to say and L, a list of edits. And for the moment, I'm not going to be very formal about how I want the list of edits to be stated, since edits seem like a complex kind of thing to state. They're probably, something about a position, and maybe doing a delete or an insert or a substitution, which needs what I'm substituting in. So I'm not going to worry about that formalism right now, knowing that the problem I'm going to be focusing on is mostly calculating E, the minimum number. Okay, so let's consider here, and I actually want to build myself my self-reduction now. So I'm going to just set it up here. I'm going to use LED for Levenshtein edit distance. And I'm going to, again, it's going to be a two-dimensional. We're going to think about considering computing substrings or converting substrings. So again, let's think of our two strings. And inspired by our two previous problems, we're going to think about prefixes. So in this case, I've got two prefixes, n minus 1, m minus 1. And we're gonna make decisions about how to recurse to those prefixes based on what we know about that last character in the same way. However, what we want to do is we now want to consider, let's start at the base case or the terminating case. Actually, I'm going to go slowly here so that we don't mess up. What happens if our n equals 0? How many edits does it take to transform A into B? So this is again A, this is B, this is of length n, this is of length m. So we said if if n is 0, that means A is empty. How many edits does it take to transform it into B? Well, B is m long, so it's actually going to take m. Now if B happened to be 0, 2, or if m happened to be 0, 2, that would be 0. And so this is different because in our last case, if n was 0, we just had 0. So let's apply that same logic. Then if m is 0, it's going to take n edits to transform us into A, or vice versa. For A, and if A is of length n and B is of length 0, we need to delete those n characters to make B. So we get n edits. Okay. So that's actually our first difference. Now we've set up our n case, our n equals 0 case, or m equals 0 case. So it looks like now we're going to be if n is greater than 0 and m is greater than 0. And now remember, we're now going to compare our last two characters. So let's compare them. And we really have a couple possibilities here. What happens if they're equal? Okay, so if they're equal, I guess that's the case I've already got indicated over here. A is equal to A. Okay, A is equal to A. So what can we do? Well, this is just like the case we had with longest common subsequence. If we have A equals to A, that means we don't need to make a change at all. That's a match. Remember, we're trying to change A into B here. We're trying to first string into the second. So that's a change we don't need to make. So we're good. So the idea is if we could change this substring, montan, into this substring, bandan, we're done. We don't need to make any further changing. So the cost, actually, if our two characters are the same, is just the cost, and remember I'm going to write this as LED, of changing the substring of length n minus 1 of A into the substring of length m minus 1 of B. So that's a fairly simple case. Now again, this is a little bit different from what we saw in our previous example. We had the same thing. If they were equal to each other, we had one case, and the one case was diagonal. But here we had this plus 1. Now we don't have a plus 1 because actually in the previous case we were counting the things they had in common. In this case, we're actually more like counting the things they don't have in common. We've switched from a maximum, the longest common subsequence, to a minimum, the minimum number of edits. So switching from a maximum to the minimum, we've sort of swapped the roles that things are playing in this problem. So in this case, there's no plus. That's actually good. That's saying we don't need any edits here. No plus 1. We don't need to make an edit to change A into A. Okay, so that leaves us with our next case. And the next case is where they don't match, right? Where they don't match. And actually the next case can be a little bit tricky. So I want to consider a few possible cases. Now the next case is a little bit tricky because there are actually 3 different operations that we can perform. A delete, an insert, and then a substitution. And each one gives us a different possible sub problem to look at. So let's just start out. I'm going to put an X here, just to change it up for us. If we have an X, we're now in this case where they don't match. Okay, so X does not match with A. So since X does not match with A, we now have to do some operation. Now again, maybe blur your eyes, don't look at the rest of the strings. We know this A, we kind of want to match it up with the next A. That'll work out good if we're able to do that. But for the moment, let's say we can't see that. We're the computer. All the computer can see are these two, the X and the A, and it has to decide what to do. Well, the option that we want is we could say, we could delete X and then transform this substring, A up to here, and into this substring, B up to here. This is doing a deletion. Do one deletion and then recursively figure out how to transform these. So in the case of our deletion, it looks like we have this subproblem, LED, where, what did we do? We took 1 off our n minus 1, m. Okay, now that would give us how many operations we would need to do to change Montana, well in this case Montana into bandana, but we want to know how many it takes to change Montanax into bandana. Well, that would take one more then, because we do one deletion to get rid of the x, and then we look up or recurse to figure out this value, transforming these two. Okay, the other possibility, let's ignore our x up here for a second. Let's say the x was down here. Okay, if we had the x down here, then what we really want to do now is we want to change, again, Montana into bandana recursively. That's where we're going to leave n alone, but we're going to cut off the x here and do m minus 1. So in my insert case, it's going to be n m minus 1 plus 1, where the idea is we change Montana into bandana and then insert the x. So that's the extra plus 1 here. So we change the Montana into bandana and then insert the x. Okay, let's consider our last case where I'm going to put an x and a y here, where basically they're both kind of useless. We want to cut both of them off. Well, the way we could do that is by doing a substitution then. We could just change x into y and then translate the rest of whatever's left in our string into the rest of whatever's left in our string. So again, if this is n and m, this would be the subproblem of LED of n minus 1, m minus 1, the same one we've got up here. But in this case, up here it was when they matched. We just said, cut them both off and leave it alone. Don't do anything else. But in this case, they don't match, so we say cut them off, but substitute. Change the x into the y, and then do this substitution. Okay. So what we actually have here is we have 3 possible operations we could do, and we don't know which one to do. So how do we pick? Well, that's usually given to us in our problem statement somewhere. We'll minimize between them. Now I'm going to make a big case here. I'm going to say, okay, LED of n and m minus 1, LED of n minus 1 and m, LED of n minus 1 and m minus 1. Those are my 3 cases. And in each case we add on 1. So I'll just add the one outside my min. Alright, so again, similar structure to our last 2 problems, but a little bit more difficult, but not too much. Alright, let's write some code. And again, our code structure should be very similar to what we've seen in the last 2 problems. So we'll start with our declaration. I'm going to call it L again. I think that's what we called it in our last couple. And let's see, our L, our index should start at 0. So let's go 0. Alright, so we'll let L be a 2D array. And we need some for loops. My first for loop, I'm going to go from 0 to n. And we're just going to initialize. And we need to be careful, unlike our last case. So i's here is going to be subbing in for n. But in this case, we're going to be doing when our m is 0. It looks like I've done this one first. M equals 0. And it looks like, in that case, it should be equal to n. And I need to be careful here. It's actually I. Remember, I standing in for our n for this loop. Okay, got another loop. Our j, going from 0 to m. J standing in for m now. So we've got L0 of j is equal to, and same thing about, is equal to j. We're done. Okay, so now we need 2 nested loops, and we'll just start where we left off. So I is going to be 1 to n, and j also is going to be 1 to m. And again, we need to do a check. So if a sub I is equal to b sub I, sub j, then we need to, let's say then L sub I j is what? Well, looks like we lost it a little bit here. If they're equal to each other, we just look at the diagonal case and copy it, no adding. Okay, so we just go is equal to Li minus 1, j minus 1. Okay, else, all right, else, well, else was this big nasty block here, all three cases. So looks like else Lij is equal to the min of L, let's be careful here, we had three cases, one's above, one's to the left, and one's diagonal. So we have I minus 1 j, I j minus 1, and L I minus 1 j minus 1. And the whole thing is a plus 1. And this one's actually a simple case to return. Our answer is just in the bottom corner like it was in the first case. Okay, once again, order n, order m, this loop here, n times m, our runtime. Okay, I think all that remains is to do a quick example. So let's take a look at one. Perhaps before we do, I just want to give credit where credit's due, I guess. We came up with this dynamic programming algorithm, but as I mentioned, Levenshtein actually came up with this recursive definition that we're looking at here. But these researchers that I have listed here on the screen are all researchers who, at least as far as we know, independently developed this dynamic programming algorithm. Now, dynamic programming was, as a methodology, was developed first by Bellman in the 50s for some applications in reinforcement learning, but that technique was applied by many others for any other algorithm that might have needed this type of technique. And most of these researchers, I don't know the history, but I'm just speculating here. Most of them probably needed to calculate the edit distance for two strings for reasons, for purposes of their research. Maybe they were in genetics, maybe they were in one of these other fields. And because they needed to do it automatically, not by hand, or maybe for long strings that would take longer, they needed a more efficient algorithm than just recursively or by hand. And so they applied dynamic programming, and they came up with this algorithm, the one that we just came up with together. And that algorithm, so we sort of independently came up with it, if you will, by working it out together. So we did what these lot did, and most of them published this algorithm, in most cases, again, I'm not familiar, I'm just assuming, not as an algorithm itself, like, hey, look at what I've done, but rather as a means to an end. I needed this algorithm to do something for me, and that's what the paper's really about. That's what these publications are really about, what they were really doing. And they just sort of as a side said, oh, to calculate, figure 3, I used this algorithm, and they, pushed it to the side. Now, because of that, the algorithm wasn't necessarily spread through the community very fast or popularized unless you were reading their reason for that algorithm. So it didn't actually basically that's one reason why it got reinvented multiple times. And today, the dynamic programming algorithm is more commonly known as the Wagner-Fischer algorithm. That's why I've got it highlighted here, but you notice that Wagner and Fischer were not necessarily the first ones to come up with the algorithm. And I'm not 100% sure why they get the credit for it, other than, I guess, if you want credit for an algorithm, maybe invent it twice in 2 years, and maybe your name will stick out. But I think, I'm not as familiar with Wagner, but I'm pretty sure Fischer is a pretty famous computer scientist who's made multiple contributions as well. So maybe, a little bit of fame helped and popularize this algorithm. So in this case, the algorithm that we just designed is also known as the Wagner-Fischer algorithm. So if you happen to looking for it again, well, a Google for Levenshtein edit distance would probably undercover it, but take a quick Google for Wagner-Fischer and you'll definitely find some information about it. Okay, that's the code we were looking at. Let's look at a quick example. And again, I've initialized my first two columns. Now remember, in this case, we initialize them with the n and the m value. So instead of all zeros, they tell us how many edits it takes. Okay. Now let's maybe focus our mind in it. This is telling us how many edits it takes to change the substring. The prefix here that's empty, say, into this empty prefix takes 0 steps. To change the empty prefix into M takes 1. MO takes 2, and so on. Into Montana takes 7. And of course, what we want to know, the one that's way down here, is how many steps it takes to change bandana into Montana. So we're going to fill in that one. All right, so going. Again, our algorithm is based off of match or mismatch. All three of our last algorithms have to do with match or mismatch. So again, we start out with mismatch. So the first line is match. Mismatch says, look at the three different subproblems and then add 1. Well, in this case, look at our three subproblems at 0, add 1, we get 1. Let's see, is this true? How many edits does it take to change B into M? Well, 1 substitution is what this is saying. That's why here, if I had my purple matrix, remembering stuff, I should remember diagonal here. Diagonal. All right, continuing, remember we only have mismatches on this first row. So again, we're looking at our three subproblems and taking the minimum. So we get 1 plus 1 here is 2. Minimum is 2, plus 1 is 3. 3 plus 1 is 4. 4 plus 1 is 5. 5 plus 1 is 6. 6 plus 1 is 7. Does it take us 7 edits to change bandana into M? Yeah, we need to delete however many, 6, whichever ones we want, and then substitute 1. That's what the last step is. We can't delete them all and then add, that would be 8. So we have to do at least 1 substitution. Okay, continuing, all mismatches, so same thing. 3 subproblems, take the minimum 1, add 1. So 1 plus 1 is 2. 1 plus 1 is 2. Does this seem right? Ba into mo, yeah, 2 substitutions. That's why we're getting this interesting pattern here, okay? But let's continue. Minimum is 2 plus 1 is 3. 3 plus 1 is 4, 5, 6, and 7. We get the same pattern again. Same thing. Can we change bandana into mo? Yeah, we have to delete 5 out and then just swap 2. There's no matches to take advantage of. Looks like we're going to get a match now, so let's see how that happened, how that helps our edits here. So again, the first couples are not, so 2 and 2 is 3. Minimum of 2 is 3 again, or sorry, minimum of 2 plus 1 is 3. But here, whoa, match, n and n is match. That's our first case we've got up here. It says just copy down, copy the 2 down. So we don't add anything here. So this is where it's saying, hey, the way to change ban into mon is only 2 edits. How do we do that? Well, it's maybe we'll recover that in a second. But 2 edits, we can see, yeah, we need to swap these 2, substitute BA into MO, but the N we can leave alone. Okay, back to mismatch. Well, now there's that 2 there, so I only get 3. Band into mon, well, again, the N is matched up, so we only have to get rid of the D and then swap the other 2 out, and so on, okay? We'll keep going then. Mismatch, N is a mismatch. Min is 4, or 3 plus 1 is 4. Mismatch, oh, sorry, match rather. Well, we have a match here, N. That just says copy it down, 5. Now notice that's the same value we would have got if we had just looked at the 3, taken them in and added 1. This is a tie. That's, if we want to dive down deep and analyze a little bit what's going on here, that's telling us there's sort of 2 matches now. We can match this N up in 2 ways and get where we need to be, okay? But finishing off, mismatch, we take the min, 5 plus 1 is 6. Okay, T is all mismatches, so just taking the min and adding. So min of 3 is 3, we get plus 1 is 4. 3 plus 1 is 4. 2 plus 1 is 3. So once the N shows up, we can take advantage of it. Mismatch again, so we take the minimum, 2 plus 1 is 3. 3 plus 1 is 4. 4 plus 1 is 5. 5 plus 1 is 6. Next row, we get our A. We're going to get some matches now. First one is a mismatch. Minimum of these 3 is 4, plus 1 is 5. Okay, we get a match. That says, again, remember, just copy down. So copy down the 4, copy down our diagonal. right? Continuing, we have a mismatch, so minimum of these is 3, add 1 is 4. Mismatch, minimum is 3, add 1 is 4. Okay, match, just copy the 3 down. Okay. Continuing, mismatch, minimum of the 3 is 3, plus 1 is 4. And a match, copy the 5 down. Okay, next row. Mismatch, we get 6. Mismatch, we get 5. Match, so copy the 4 down. Mismatch, well, they're all 4s, so plus 1 is 5. Mismatch, we get a 3, we'll get a 4. A match here, copy the 3 down. See that 3 is making its way down. That's the 3 that we were looking for. Mismatch, we get 4. Okay, last row. Mismatch, 6 plus 1 is 7. Here we have a match, so we'll copy the 6 down. Mismatch, so we have minimum of these 3 is 4, plus 1 is 5. Mismatch again, 4 plus 1 is 5. We have a match. In this case, we copy the 5 down. Mismatch, minimum of these 3 is 3, plus 1 is 4. And finally, our last match, where we get our 3. Now, the way we finish this off, the 3 is our answer. It tells us 3 is our edit. Now, this is one interesting case where it depends a little bit on why we are applying this edit distance measure. In some cases, we might want to know how to actually transform one string into the other. Although if you're using this even in, say, spell checking, you don't actually delete or edit the string. You just swap it out. The program will probably just swap out one string for the other. However, in other applications, as I mentioned, say we were doing this to compare how close 2 genes are or something like that, then really the number is all we need at the end. We don't care how to recover. We just want to know these are 2 close or these are 10 close. We use that measurement in some other calculation. If that's the case, we're done. However, if we need to know the edits, then we might have wanted our purple matrix, which I didn't include in this example. If our purple matrix would remember either diagonals or diagonal left or rights like we have here, or sorry, diagonal left or ups like we would have for this subproblem. So let's see if we can recover this now. Now, if we're going to do this, we actually unwind. We have to keep doing this, but backwards. We're going to start here, and we're going to think, what happened in this case? In this case, we had a match, so we must have we must have done nothing. And in a case of a match, where in this case, that A is something we don't need to change, so we use it in the final product. So we skip it. And in that case, this subproblem says I minus 1, j minus 1. That tells us go diagonal. So we'll backtrack. We get to here. Okay, we go to this one. Well, how's this one? It's a match too. Same thing. So we'll backtrack. Okay, we leave that one alone. So far, no edits made. Okay, again, A match. All right, we get to here. Okay, but here, when we're here, we now have a mismatch. So we now know in this case, where our T and our D. And in that case, we took the minimum of our 3 subproblems, which also was diagonal. The diagonal case in our 3, remember when we set it up, here it is, our diagonal case, was the substitution case. That was the one that told us change our D into our T. So that's one of the operations we need to do according to this. Nothing, 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 change a D into a T. Okay, this was another match, so do nothing. And this was change an A into an O, change a B into an M, and we're done when we get up here. This was a special case where we went all the way diagonal. And the reason we went all the way diagonal on this one was 2 things. We had matches, which are diagonal, or only substitutions. Okay, only substitutions. If we were doing deletions, that would lead us to the left. And if we were doing additions, that would lead us up. Okay, but we didn't have any that went left or up in this example. Okay, so once again, edit distance is used in all kinds of disciplines, not only in computer science. It's not only just used on English strings as well, it's used on all kinds of stuff like DNA. And so you might see this come up in other applications that you might encounter in the future, calculating the edit distance between 2 possible strings. So we've seen a couple different examples of how to do that. The longest common subsequence can be used in that, or Levenshtein's edit distance, as we looked at here. And we've seen now 3 good examples of two-dimensional dynamic programming. In my next couple of videos, I'm going to once again look at some two-dimensional dynamic programming for a couple other problems that might be of interest. So thanks again for watching, and we'll see you in the next video.